This is Nick Fryer, and today we're talking about Physics 1 Lab 3, which has to do with gravitational attraction between different masses in space. So just as an introduction, there were two parts to this lab. The first is to find the mass of a black hole where we know the mass of a star that orbits around it. And for part two, we have to find the initial velocity that a spaceship must leave a planet at in order to get close to that black hole, but not collide with it or the planet. Just as a preview, for part one, we found that the mass should be 8.78 times 10 to the 33 kilograms, and that the initial velocity that the spaceship leaves at in part two is minus 3.1 times 10 to the 7th, 2.8 times 10 to the 6th, 0 meters per second. So as part of the introduction, some key concepts. The first one is Newton's second law of motion, which says that the net force on an object is the change in momentum over the change in time, or dp/dt. And that can be rearranged to find our velocity and position update formulas that we know and have used in the past. Just note that because gravitation is a non-constant force, we use V final instead of V average in the position update formula. So we also have to talk about the parallel and perpendicular components of a net force. The parallel, or p hat direction, refers to the changes in speed. That's what causes the changes in speed. And it's parallel to the direction of motion. In the perpendicular direction, or n hat, this causes changes in the direction of motion, and it points to the center of the kissing circle, so towards the direction that the object will be turning at. And the relevant equations can be shown below. In part three, we talk about gravitational force, which is big G times the two masses over the distance between them squared, and then times the negative version of the unit vector that points from one mass to the other. So in part one, our system is the star and the surroundings of the black hole. The star has forces being acted upon it by the black hole. In part two, the system I consider to be the spaceship and the surroundings of the black hole and the planet. We do focus on the planet as well, but mainly we're focusing on the spaceship and what velocity it must leave at. So that's what I consider to be the system. In part one, the initial conditions can be seen here. Note that we just plug in G and the mass of the star that are given to us. Delta T is 24 times 60 times 60. And this is just converting from a normal second that we know to the amount of seconds in a day. So we did use an iterative coding technique here. We start with our initial velocity, which we can then multiply by mass to find the initial momentum. We find finals of both of those, and then we can calculate our F net as normal. And then we can introduce our new ideas to find the parallel and perpendicular components of our net force to ultimately find the mass of the black hole. So when we did this, this is the video here. Note that the force vectors are largest closest to the black hole, which is what we expect because the distance is less. You can see the different magnitudes of the forces at the final position, but ultimately we found that the mass of the black hole was about 8.78 times 10 to the 33 kilograms. And this is just by taking the numbers that the model generates for us and averaging them out. So just as a discussion, the net force changes depending on the distance between the bodies, which is what causes the elliptical orbit. So when you're further away, you have less force and vice versa. And the sources of error are that there's a non-zero delta T at each iteration and that we rounded values. So G, we said, was approximately 6.7 times 10 to the negative 11th, and etc. So the net force and parallel and perpendicular components do not differ from the rate of change of momentum and its components. They're exactly equal. Just keep in mind that if we're talking about momentum, we need to know the mass, the velocity, and the time, and so on. So the initial conditions, we plug in the mass of the black hole from before, and we know everything else. And then we can ultimately find the X and Y components of the velocity by trial and error to make sure it gets as close to the black hole without actually leaving it. And we code the relevant equations just like before, iteratively, except this time we're talking about gravitational attraction between the black hole and the planet, the ship and the planet, and the planet and the ship. And then we kind of add everything together to ultimately get our planet velocity and position update formulas. And these are the results. So you can see it gets close to the black hole, but eventually leaves. And this is with the initial velocity that we said before. And the shortest distance between the ship and the black hole is about 5.8 times 10 to the 8th meters. Just as a discussion, like we said, this is the initial velocity. It moves more left than up because the magnitude is larger in the x direction. So our gravitational force is maximum at the shortest distance between the spaceship and the black hole because there's a higher there's just less distance, and sources of error are the same as in part one. And this is what I found by some trial and error. My velocity could be if I wanted to make the spaceship orbit around the black hole, so it's more up and less left than before.